recorded, and now we're just going to record the rest of today's. So simplifying each radical expression, adding or subtracting radicals, they need to be like radicals. And so root 8 is 2 root 2, and root 18 is 3 root 2, and root 32 is 4 root 2, and that's 9 root 2. Okay? So I'm not going to go into huge detail on all of these, like root 8 is 2 root 2 because root 8 is the root of 4 times 2, which is root 4 root 2, which is 2 root 2. Okay? If I make any mistakes, let me know, but otherwise just accept that probably what I've written here is correct, and then if you want to look at it, so when I say 4 root 12, and okay, so that's 4 times, root 12, so here's my thinking, right? I just do this in my head. 12 is 4 times 3. So it's the root of 4 times 3, which is root 4 root 3, or 2 root 3. 75 is 25 times 3. Root of 25 is 5, so this is 5 root 3. 48 is 16 times 3, and the root of 16 is 4. So root 48 is 4 root 3. Okay. Now again, you may want to show more detail on this stuff. You actually need this stuff. You may want to show more detail on this stuff, and that's fine. It's whatever works for you. Okay, so this, we put a little equal sign there. So this is 8 root 3 plus 5 root 3 minus 8 root 3, which is 5 root 3. Okay, now, you could check this, and how would you check this? If you want to know, how do I know I'm right? Okay, you can just plug this in your calculator. 4 times root 12 plus root 75 minus 2 times root 48, hit enter. 5 times root 3, hit enter. If they're the same, then you know that you've done it correctly. If they're not, you made a mistake somewhere. And sometimes when you make a mistake, the mistake could be in the checking, and the mistake could be in the working out, right? So that's what you have to sort of figure out. Okay, root 10 times root 20. When we multiply radicals, it becomes the root of 10 times 20. Where that can come from. So you just put them together under the radical sign, right? Which makes this the root of 200, which is 10 root 2. Now, seeing they gave this to me twice, I don't know if it's in yours. Is it down on yours twice as well? Yeah, okay. Well, let's do it a different way then. So root 10 is just root 10, right? I can't simplify that. But root 20 is 4 times 5. So this is 2 root 5. So this will give me 2 root 50. But 50 is 5 root 2. And we get 10 root 2. All roads lead to the same answer, right? There is only one simplified answer for this. Okay. And how you get there really doesn't matter. What's happening here is basically 10 has a factor of 5, and so does 20. Okay, but you can't take them out, right? You can take the 4 out and get 2 root 5. When these 5s combine, then you've got that 25, right? So you got a 5 from here and a 5 from here, and also a 2. But you get that 25, and that 5 can then come out. 2 root 6 times 5 root 18. So I can simplify first. This is 2 root 6, and this is 5. Root 18 is 3 root 2. Okay, now what do we do? Well, okay, let's simplify again. So 2 root 6 times 15 root 2. And now you multiply the numbers outside. So 2 times 15 is 30. Root 12. Root 12 is 2 root 3. So this becomes 60 root 3. F, monomial times binomial. Okay, so multiply. And also on this one, you could have just gone 2 times 5 is 10, and then 6 times 18 is whatever 6 times 18 is. But then the numbers get a little bit harder to figure out what perfect squares. So if you can reduce something, right, simplify it, then it just makes it a little bit simpler at the beginning. Root 2 times 3 root 2 is 3. Now some people might want to think 3 root 4. So you know what, I'm going to write that out for you. 3 root 4 plus 2 root 10. Okay, so that's just a straight multiply, we're foiling it. Root 4 is 2 times 3 is 6, bless you, and then plus 2 root 10, right? Nothing you can do with root 10. Okay, doesn't simplify, right? There's no perfect squares that go into 10. Next one, so again, same deal, right? We've got a monomial times a binomial. 3 root 10 times 3 root 5, you multiply the numbers together. 9, you multiply the radicals together. 9 root 50. Minus 3 root 20. Root 50 is 5 root 2. Root 20 is 2 root 5. Gives me 45 root 2 minus 6 root 5. Okay, no like radicals, nothing we can do to simplify any further. What you're always looking for in simplified form is, like when you're looking at this 12 here, you're saying, are there any perfect squares that go into 12? Yes, there is, right? There's a 4.
Can you go over that one again?
Last one?
Yeah.
Okay. So 3 times 3 is 9. Root 10 times root 5 is root 50. 3 times 1 is 3, and then you get root 20. Root 50 is 5 root 2, okay, because it's 25 times 2. All right. So you guys may want to break it down further. I'm not doing that here, but you can always replay this tonight and look at it and say, how, okay, I got to work the root 50, right? So you might sit down and say, okay, what is that? Oh, it's 25 times 2. That's what it all comes down to. Okay, I'm not showing that in this. All right, I mean you are supposed to have those basic skills. So you might have to sit. You might want to sit down and go through this again and do this if you need to, right? Because you need to look at it and say, because we should get to the point where you look at root 8 and you just write down 2 root 2. You don't really have to think about it a lot because you're going to see a lot of root 8s. Or you look at root 50 and sort of the same thing. Oh, give me the eraser. Like I have an eraser which doesn't erase. Nice. Let's go with this. That works a little better. Can I get that? All right, see? There's going to be junk left there. This is 2 binomials, right? So we're going to FOIL it out. It's actually a difference of squares, right? So we're going to get root 5 times root 5. Root 5 times root 5 is root 25, but instead of thinking of it that way, when I multiply a radical by itself, I just drop the radical sign. So root 5 times root 5 is 5. Root 5 minus 4 root 3 gives me minus 4 root 15. So that's first, right? Root 5, then outer, then inner. This will be plus 4 root 15. So these guys are gone. And then we've got minus 16 root 9. Okay. Usually, sometimes I don't do that. In this case, I'll do that. So that's 5 minus root 9 is 3. 3 times 16 is 48. Okay. So root 9, 3. 3 times 16, 48. These are called conjugate binomials. Some of you may have done this where you rationalize a binomial denominator. You do it by multiplying by the conjugate, right? And what it does is it removes any radicals, right? And the reason is because the only radicals come from the outer and the inner products, and they're the same but with opposite signs. Okay, this one, that's not going to happen. They're not conjugate binomials, right? We're going to get. So we start off, we get root 18 minus 4 root 12 plus 2 root 9 minus 8 root 6. Okay, so we're foiling, that's 4 products, right? And now we're going to simplify each radical. So root 18 is 3 root 2. Root 12 is 2 root 3. Root 9 is 3. And root 6 is root 6. Right? No, you can't do anything with the 6. There's no perfect square that goes into 6. So we get 3 root 2 minus 8 root 3 plus 6 minus 8 root 6, and we're done. Okay? There are no like terms. There's nothing to collect together, right? I've got a root 2, a root 3, a root 6, and just a number. Okay? So there's no collection. We just end up with 4 products and nothing that collects together. It's not like this one, certainly, where we had 4 products as well. Right. Anytime you multiply 2 binomials together, there will be 4 products. Okay. And then stuff happens. Either they collect together, or in this case, they don't. Wait, leave that a little bit for you. Simplify, i.e. express with rationalized denominators. So anytime we see a radical in the denominator, we need to get rid of that radical. The way we do this is to rationalize, and the process is to multiply by whatever the radical is. If I multiply root 3 by root 3, it just becomes 3. Now I can't just put a root 3 down here if I multiply this. So I multiply by root 3 over root 3, which is equal to 1. When you multiply by 1, are you changing anything? No. So we're changing its form, but not its value. And so its form is going to be 6 root 15 over 3. The 3 goes into the 6 and gives you 2 root 15 as your final answer. Okay, so that's simplified. How do you know? Well, there's no radicals in there, right? I mean, there's nothing that simplifies with the 15. 15 is 3 times 5, no perfect squares. On your calculator, you can go 6 root 5 divided by root 3, hit enter, and you can go 2 root 15 and hit enter, and they will be the same. Okay, and then you know, oh, okay, yeah, I did that one right. Now, if you're going to check that way on a quiz or a test, do it at the end, right? Like, finish everything off. Don't do it in the middle, or otherwise, you know, you get to the end and it's like, hey, time's up, hand me. No, you're only half done. So if you're going to do any checking like that, do it at the end. And by all means, if you finish early, then go and check that, right? I mean, check stuff out. Root 8 over 2 root 6. Going to multiply by root 6 over root 6. Gives, well, actually, you know what? We can simplify a bit first. See if I can get the eraser out. Yeah, except for that piece. No, now it's gone. Root 8 is 2 root 2. So the 2's are going to cancel. Okay? And that leaves me with root 2 over root 6. That actually can be simplified, but I don't need to right now. And I'm going to multiply by root 6 over root 6, giving me root 12 over 6, which is 2 root 3 over 6, which is root 3 over 3. All right, so anytime we get an entire radical, we want to express it as a mixed radical, if we can, right? So root 12 becomes 2 root 3, and then the 2 goes into the 6 3 times. Okay, again, check on a calculator, go root 8 divided by 2 root 6, go root 3 divided by 3, should be the same. This one, we're going to multiply by root 5 over root 5. So we multiply by whatever radical's in the bottom. Here we could have just started by multiplying by root 6 over root 6. Right? You would have got root 48 over 12. And the root 48 would become 4 root 3 over 12, which would become root 3 over 3. So it's still going to simplify down to the same answer. Okay. This is binomial times monomial, so we get 2 root 10 minus 5, right? So 2 root 10 minus root 5 times root 5 is just 5. And on the bottom, just 5. Now it's tempting to say, hey, I got a 5 there and a 5 there. I want to. No, you can't. Okay. The only way that you can cancel this 5 is if there's a 5 here as well. And that's not the 5 that's part of the 10 that's under here. That's not allowed to cancel. So 5 has to be a common factor of all three things. In an expression like this, if you want to cancel, the same number has to divide into this, this, and this. Which in this case, it doesn't. So that's it. Okay, simplified radical expression. So, in this case, what we're looking at is we've got variables underneath the radical sign, right? We're either doing, it doesn't look like we have any cube roots, so they're all square roots. So what we're looking for is perfect squares. So this one I'll show a little more detail. So what I want to do is I want to write 45x to the fourth as a product. And I want to split the 45. Is there a perfect square that goes into 45?
Bless you.
Bless you. I'll take that as a yes. And what is it? 9. Okay.
Sorry.
Does x to the fourth have a square root? Yes, it does, right? So what I'm doing is I'm putting down the factors of 45x to the fourth which have square roots. So 9 is the number, and x to the fourth is the power of the radical. And then what's left? Well, 5, right? Because 9 times 5 is 45. So now I'm going to split that out too, and I'm going to write the stuff that has a square root separate. So I'm going to write it as the root of 9x to the fourth times the root of 5. And what's the root of 9x to the fourth? 3x squared. Thank you. So we end up with 6x squared root 5. Okay, so this time, I mean, all we've done really is introduce. If I'd said root 45, I would expect from you 3 root 5. But we've got that x to the fourth in there, so we say, okay, I need something that has a square root, which is x to the fourth. So this, 5x to the fifth, what's the perfect square that goes into 12? Okay, I'd wait, but I'm not going to. I'm going to write 12x cubed as 4, because that's the perfect square that goes into 12, and x squared, because x squared has a square root, right? X cubed doesn't. X to the fourth does. X to the fifth doesn't. X to the sixth does. Any even power of x has a square root, right? You just take half. You have the power, right? You take half of the, if you're doing the square root of an even number, you just take half of it. So I've split the x cubed up and write it as x squared times x. This part has a square root. This part does not. It'll still be under a radical sign. So I get 5x to the fifth, and now I split my root. And now I take the root of 4x squared, which is 2x. And we just multiply and get 10x to the sixth root 3x. Okay, so you will run into this stuff occasionally, right? You'll be using formulas in, whatever area of study you go into. There's going to be formulas, there's going to be math, and there's going to be formulas. There may be radicals involved, right? And you may have to simplify things. Okay, root x is just root x. There's nothing you can do with that. Actually, I guess what we should do is let's multiply this together. So we get negative 5 times 2 is negative 10, and they get the root of 8x to the fourth. right? So root x, and then the x cubed times x gives me x to the fourth. Uh, 8x to the fourth, the 8 has a perfect square that goes into it, which is 4, and x to the fourth is a perfect square, right? So we put it together. Gives me negative 10, root 4x to the fourth, root 2. And this will be 2x squared, root 2. And there's our simplified form, right? Negative 20 x squared root 2. Okay, last two. Solving equations. So solving a radical equation. The way that we solve a radical equation is we try and isolate the radical, get it by itself, and then we square both sides. So in this case, radical's by itself, square both sides. X plus 5 equals 144. X is equal to 139. Okay, just subtract 5 from both sides. Now, the thing is, whenever you solve a radical equation, sometimes you can introduce extra solutions, right? By the act of squaring both sides. You introduce a solution that isn't really a solution. So you need to check. So check. Room here. So the way I check, I do a left side, right side check. You work the left side separately, and this is called a t-table. And so I'm just going to substitute in. So 139 plus 5 equals root 144 equals 12, and that checks. Kind of squeeze that in at the bottom there, right? I mean, if you have more room, obviously, you can go a little bit further down. But that checks, right? It's okay. It works. This one, before we square both sides, we need to get rid of that minus 1. Okay? We're going to do that how? We're going to add it to both sides, right? So we're going to get 9 is equal to the root of 2x plus 7. Square both sides. 81 is 2x plus 7. 74 is 2x. X is 37. And we got to check. Left side is equal to 8. The right side is equal to the root of 2x plus 7 minus 1. So 2. Now is where I put in my number, right? 2 times 37 plus 7 minus 1, which is root 81 minus 1, 9 minus 1, 8, and it checks. Okay, any questions? I'm just going to stop.